we will learn about impulsive loading and Duhamel's integral. And the major objective is to see that how this can be used as a tool for finding out the response for any general type of uh, forcing function. That means if there is an arbitrary variation of the forces, it may be due to an earthquake or due to maybe any other thing where we are only having the data, then even we can, the time versus acceleration data. So even under that, how we can try to have the response of the system. Okay, and these Duhamel's integrals will be a tool for that. And then if the force is given analytically and integrable, then possibly we can carry out the direct integration and we can get it and get the response. Or even if it is not given through any analytical expression, it is given through numerically, the acceleration versus time data, then we can carry out the numerical integration of the Duhamel's integral, and then also we can have the result. So this is a more generalized method. So far we were discussing about the fourth vibration which is created due to harmonic or exponential um, time varying force. But now we are just trying to see that which is more general one, and how the concept behind that has been developed. Well, let's have a look as a principle to understand what an impulsive load is. An impulsive load is one that is applied during a short duration of time. Okay, that is the specialty of the impulse. And in fact, you know that there are some kind of impulsive load. We have just tried to show it. It may be a very small interval, and the load can be like this, or it may be triangular, it may be rectangular. So, but it will act over a very small interval of time. So as a result of that, it will change the momentum. Okay, so the change in moment, impulse always create. If you just give a hammer blow to a system, so it will change the momentum of the system, and until and unless there is any external force, so the system will move with that momentum. This comes from the Newton's law. So so what we'd like to say that force which has a large magnitude and acts during a very short time duration, such that the time integral of this force is finite, is known as impulsive force. I mean, that is one of the characteristics. In many practical situations, the forcing function is neither harmonic nor periodic. That means it may be any erratic function. Some of the example of the impulsive loading is high velocity impact, blast loading, design of certain classes of structural system. For example, vehicles such as trucks or automobiles or traveling cranes. Okay, so you have seen that the JCPs are working on the road, so those are sometimes may create some kind of a impulsive loading, a sudden jerk. So uh, we would like to see that how we may try to use the concept of impulse for getting the response of a system when it is subjected to any general type of force. So here we are just seeing that there is any general curve which is a function of tau, and the force is varying as a function of tau and is given by f tau. Now, if you consider that at any value of tau, there is a small increment in tau, so from tau to tau plus d tau, then you know that this loading we may consider as an impulsive loading because the time interval is very small. Therefore, the total impulsive load, impulsive, the effect of the impulsive load is integration of f dt. So the in, the impulsive load, particularly over this infinitesimal time interval d tau, is f tau d tau. Is this understandable? Now you try to imagine that if we consider that these forcing function, the area under this forcing function can be uh, considered as a combination of small such strips. That means, say here up to this, up to an infinitesimal value d tau, we take a strip, and then we may call that that is an impulsive load which is acting on the system. Then there is a next strip, so that strip also another load which is acting on the system. So that way, for each of such, that means if we divide it into a large number of infinitesimal strips, and for each of the infinitesimal strips, we consider each of the infinitesimal strip is an impulse, and for each of these, if we can sum up or integrate the effect of the response at the time t, then possibly we'll be able to get the response due to the total forcing function varying in this way and in an any arbitrary way up to a time t. That means time t, up to time t, we will keep on integrating. We will keep on adding to it, and then tau is the current variable which is varying from 0 to t. That means for each of, see, this strip at this time t will have some effect because it will create some change in momentum, and a change in momentum means mass cannot change, so the velocity, it will create a change in velocity, and because of the effect of the change in velocity there should be a response at time t. Similarly, each of these strip as an impulsive load will have an effect, will introduce some kind of change in velocity, and that effect will have uh, some contribution into the response at time t. So that means all these effects should be summed up to the time t. That means this tau will vary over an interval from 0 to t. So let us proceed further. So from the Newton's law of motion, we get that m dv dt equal to f tau. Okay, that means dv dt is the change in velocity d tau, and m into this change in velocity is equal to the force. Okay, because dv dt means acceleration. So mass times the acceleration is equal to force. All of us know that. So, and that acceleration is dv dt. That means dv will be f tau d tau over m. So that means if we consider an impulse ft dt acting on the structure represented by the undamped oscillator, and then at the time t, the oscillator will experience a change of velocity given by dv. These change in velocity is then introduced in equation of undamped oscillation. That means, say if I think it just separately. For the time being, I'm thinking that only this strip is there. This impulsive load is there. So for this impulsive load, what will be the response at time t? See, that impulsive load will create a change in velocity dv, which is equal to f tau d tau over m. And then that means that change in velocity will be considered as an initial velocity, and because of that initial velocity, whatever free vibration will take place up to the time t, that will be the response at the time t. Am I able to make you understand? We know that the displacement y is given as, if the initial displacement is y0 and if the initial velocity is v0, then the response is given by y equal to y0 cos omega t plus v0 over omega sin omega t. Now in here, when we are applying impulsive load, then what is happening is it is not creating any initial displacement, but it is creating initial velocity. So that means only this v0 over omega sin omega t, that will be valid. So how much will be this v0 by omega? You see, this v0 will be substituted by this dv, because it is, the interval is very small. Therefore it will be ft d tau over m omega. Okay, so that means just we are substituting this value of dv over here, and then here it will be sine omega t minus tau. Why it is t minus tau? Because you see that the impulse is acting here at this point of time tau. So it has introduced the initial velocity uh, at t equal to tau, and then the effect of that has acted over the and has created some initial velocity which has initiated free vibration, and that free vibration is acting over, if we are interested in getting the response at time t, that means that free vibration after an interval of t minus tau should be calculated. So then only we will get the response for this trip. So this way, for if we consider that we have to sum up the responses for each of such impulsive load acting over in very small or infinitesimal time interval, then uh, to have the response together at t, we have to sum up the response for each of these strip, and in each case the time duration, the effect of each of the strip will be calculated at a time length of t minus tau, and then it should be added. Am I able to make you understand? So what is happening is dyt is coming as this, and see here it is d tau. So that means there should be an integration to get the value of the response at time t. So it becomes yt equal to 1 over m omega, and then the integration, because this tau is varying from 0 to t, so this integration will be valid over 0 to t, where d tau will be a current variable, and it will be f tau into sine omega t minus tau, and then this f tau is, sorry, this f tau is the force what we are getting here at for any current value of tau. And so if we can analytically carry out this integration, if f tau is such a function that this is become an integration is possible, is an integrable function, then we will do it. We can make analytical integration. If it is not possible, then we can make numerical integration, and this integral in this equation is known as Duhamel integral. So that means we are using this concept of the integral, we are trying to utilize the concept of this Duhamel's integral for getting the response for any general type of loading. If tau can be any function, if analytically it is possible, we will evaluate the integration analytically. If it is not possible, we will evaluate the integration. We can carry out the integration by numerical methods, as you have learned in the numerical methods. There are a lot of methods available. and uh, then so this is the effect of the force. Now apart from this, if initially when the system when the this force is applied and the system has started receiving the force, before that if it has any initial velocity and initial displacement, so for that another free vibration will be added. So that means to make it more generalized, if the initial mm, velocity and initial displacement is given, then for them again this part will be added y0 cos omega t plus v0 over omega sin omega t plus this integral. And so in this way you will be able to calculate the displacement, I mean displacement as a function of time, by carrying out this integration either analytically or numerically. Is this understandable to everybody? Okay.